going to discuss chemical equilibrium. So when we're talking about chemical equilibrium, we first need to look at reversible reactions and what that means for a reaction to be reversible. If you say that a reaction is reversible, that means that the reaction occurs simultaneously in both directions. So it can go forward and produce the products, and the products can then in turn go reverse and produce the reactants. So it goes back and forth. We have products being produced and we have reactants being produced at the same rate. When both the forward and reverse reactions are occurring at the same rate, we call that chemical equilibrium. So where the rate of the forward reaction is equal to the rate of the reverse reaction, equilibrium has been met. The equilibrium position is given by the relative concentrations of the products versus the reactants. At equilibrium, the concentration does not change. So what ends up happening is we end up having something like a graph that might look like this, where we have our concentration. And if this is going to be our concentration, we start with our products and they'll come down, and we can start with our reactants and they'll go up. At this point where the concentration of our products and our reactants are no longer changing, so you've got this flat line, that's where equilibrium happens. Now, when we're looking at equilibrium, this is a dynamic process. So it's a constantly moving, constantly shifting process. And when we're looking at reversible reactions, that's where the products are able to turn back into the reactants. When I say reversible reaction and I say shifts to the right, or our reaction shifts to the right, what that means is that our forward reaction is favored, where our reactants are producing products. When I say shift to the left, that means that the reversible reaction is favored. And what that means is that more reactants are made. So shifts to the right would be this blue line, shifts to the left would be that orange line. And again, remember, we're talking about reversible reaction. So we have a forward reaction and a reverse reaction. Now, when we're looking at equilibrium, we've already talked about this, and I drew up this graph a little bit earlier. But when we're looking at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So in this case, you have equal rates, okay? And you can see that in this very first graph. Those rates have met up and are equal, okay? Now, when we're looking at a graph where we're looking at amount or concentration over time, we are looking at equilibrium has been established when those lines have become parallel to each other, okay? So at equilibrium, there's no change in the amounts. Now, you'll notice that your reactants, we've started high with our reactants because that's how you start a reaction. And the reactants are producing products. So the reactants go down as the products go up. Okay. And then when those no longer shift in their concentration, that means equilibrium has been met. Now, what you could have is you could have the reactants go there and the products go there. Okay. You could have something like that where they don't end up crossing, and that's fine. In this situation, this just means that, like in this graph up here on the top right, that just means that the production of reactants is favored. So going through these notes real quick, just to make sure that we've hit all of the points, a situation when the forward and the reverse reaction rates are equal, that's when equilibrium has been met. At that point, the reactants and the products remains constant. So the concentration of the reactants and products is constant. Now, notice they're not the same, but you do have, in this case, you have the concentration of the reactant stays constant and the concentration of the product stays constant. Equilibrium is a dynamic process, meaning that it's constantly moving, it's constantly shifting. Okay, even though it may appear like it's not. So sometimes you might have more of the products than the reactants, but you probably saw that a lot with your PhET lab, or you'll see that in your Gizmo, where the line, the graph got very jagged, and it gets very jagged because it's a dynamic process. How do we measure equilibrium? Well, we measure equilibrium with what's called an equilibrium constant. And the equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants. The concentration, remember, that's what this bracket means, the concentration of the products divided by the concentration of the reactants. So in this case, we have our products are here, are our CC and DD, and that lowercase c right there, that represents the coefficients from the balanced chemical equation. So we have the concentration of C raised to the power of that coefficient times the concentration of D raised to the power of that coefficient, all divided by the concentration of A to the A and B to the B. So again, concentration of the products divided by the concentration of the reactants. And we're going to look at some practice problems on how to calculate that in a few slides. Now, when KEQ, or the equilibrium constant, is greater than 1, that means that the forward reaction is favored, or that the production of the products is favored. So you can see that in this diagram right here. That diagram shows that we have a production of more products in the end than the reactants. Okay. Now, what does that tell you? Well, greater than 1, that means that your numerator is greater than your denominator, and that's true. 5 divided by 1 is a number greater than 1. 2 divided by 1 is a number greater than 1. 5 divided by 2 is still a number greater than 1. Now, what if the reactants are favored? If the reactants are favored, that means that your denominator is greater. And so that means that the production of the reactants is greater. And that's going to be this situation. So this diagram right here shows that the production of the reactants is favored. There's more reactants present. When KEQ is less than 1, that means that the reverse reaction is favored. So when you are writing your equilibrium expression, remember, KEQ is equal to your products divided by your reactants. Okay. And so when we're writing our equilibrium expression, please note that you do not include solids and you do not include liquids. Okay, they do not appear in your equilibrium constant expressions. They are assigned a value of 1. Also, catalysts are not going to affect the equilibrium position. Catalysts are going to speed up the reaction, but catalysts are also going to speed up the reaction for both the forward and the reverse reaction. Remember, in our last video, we have our reactants and we have our products. Well, a catalyst is going to lower that activation energy. Okay. Well, if it lowered the activation energy for the forward reaction, it also lowered the activation energy for the reverse reaction. So a catalyst will not affect equilibrium, but temperature, your equilibrium constant can shift if your temperature shifts. Let's go ahead and look at this practice problem. This practice problem is talking about N2O4 dinitrogen tetraoxide is a colorless gas and nitrogen dioxide is a dark brown gas. They exist at equilibrium with each other. At equilibrium, the concentrations are going to be N2O4 is 0.65 molar and NO2 is 0.012 molar. So what I'd like for you to do is calculate the KEQ. You want to determine, do you have more products or more reactants? And is the forward reaction favored or the reverse reaction favored? So let's take a look at this calculation. First, we have from our balanced equation. Remember, we had our equation was N2O4 and our product was NO2, and there were 2 of them. Okay, so we end up having the products squared divided by the concentration of the reactant. So I do 0.012 molar squared divided by 0.65 molar, and that's going to give me 2.2 times 10 to the negative 4. So that gives me a KEQ of less than 1, which tells me that more reactants are favored. There's more reactants. Okay. And then also that tells me that since we have more reactants, that tells me that my reverse reaction is favored. My reverse reaction is favored. So if KEQ is less than 1, the reverse reaction is favored. So let's go ahead and take a look at some practice problems. In this practice problem, the first one, we have the reaction of 2H2 plus O2. If H2 is being consumed at a rate of 0.42 molar per second, at what rate is O2 being consumed? So this goes back to reaction rates. And remember, in our explanation of reaction rates, we're just using stoichiometry here. So we have 0.42 molar per second for H2. And so I'm going to multiply by my mole ratio. For every 2 moles of H2, I have 1 mole of O2. So if I divide that by 2, I'm going to end up getting 0.21 molar per second for O2. Okay. And then if I'm looking at what rate is H2O being produced, well, I have a 2 to 2 ratio or a 1 to 1. So that's going to end up giving me 0.42 molar per second. Okay. Now, in my next question is dealing with our equilibrium constant expressions. So N2 plus 3H2 yields 2NH3. The first thing that I want to point out is we're going to not include anything that's liquid or solid. In this very first one, I don't have that problem. So I have my KEQ is equal to my products, which are NH3, and NH3 is raised to the power of 2 divided by the concentration of N2 times the concentration of H2 cubed. Okay. Now in my next one, I have 2 KClO3 yields 2 KCl plus 3O2. But because I've got this solid here, I'm not going to include any of my solid. So my KEQ for that one is going to end up being the concentration of O2 cubed. Okay. And then if I look at my next one, I have H2O liquid. So liquid's not going to be included. So I'm going to say KEQ, products over reactants. My products are my H plus and my OH minus. Now, this might look very familiar because we just talked about this. This is the water ion product, okay, or that was the KW. Okay, so let's look at this next question. It says determine the KQ if given these values. So what I'm going to do is I'm going to take these values and I'm going to plug these values into my equations above. So if I go above here, I have NH3 is 0.01, 0.01 squared divided by 0.02 times 0.02 cubed. Okay. And so I'm going to go ahead and calculate that out. I'm going to end up giving me a value of 625. And then for my next one, I have O2 cubed. So 0.05. And I'm going to cube that. 0.05 cubed is going to give me a value of 0.05 cubed is going to end up giving me a value of 1.25 times 10 to the negative 4. Okay, so in these two cases, here I have my KEQ is greater than 1, and here I have my KEQ is less than 1. So in that case, I have my products are favored, and then in this case, I have my reactants are favored. Okay. The last thing that we're going to look at today is equilibrium and Le Chatelier's principle. So Le Chatelier's principle states that if there is a stress in the system that is in equilibrium, if there's a stress on the system in equilibrium, then the reaction is going to shift in a direction to relieve that stress or that added pressure. So if a stress is applied to a system in dynamic equilibrium, the system changes to relieve that stress. Now, that stress can be changed in terms of concentration, temperature, and pressure. Okay, so in terms of concentration, if I increase the top concentration of the reactants, that will cause the reaction to shift and produce more products. If I increase the concentration of the products, then it will cause a shift for the reaction to shift to produce more reactants, so shift to the left. If I remove some reactants, then that's going to end up causing it to shift to produce more reactants. And if I remove products, it will cause the shift to go to the right, which is going to be to produce more products. So what I mean by that is, say I have this reaction where I have reactant A, I have my balanced equation, B, and I have reaction with the products D and D. If I add more A, then what's going to end up happening is I'm making it unbalanced. So if I think about it in terms of a seesaw, here's my balanced equilibrium, okay? If I add A, it's going to cause it to be less balanced. So now I've increased A and B, and I need to increase C and D to get it to be back to more balanced. So what am I going to do? I want to shift to the right to produce more products, okay? And then that's going to bring it back to being balanced. Now, let's say that I have my seesaw and I remove, so I have it like this, and then I remove some C. Okay. If I remove some C, then what's going to end up happening is it's going to be like this: C, D, and A, B. And so what do I need to do? I need to produce more products in order to bring it back to this equilibrium position. Okay. So if I increase on a side, I'm going to shift away from that side. If I decrease on a side, I'm going to shift towards that side. And when I say shift, that means shift right is the forward reaction, shift left is the reverse reaction. So what about temperature? Increasing the temperature will cause a reaction to shift away from the side of the energy in a thermochemical reaction. So if it's exothermic, then I'm going to increase the temperature. That will cause it to shift toward producing more reactants. If it's endothermic, increasing the temperature will shift towards producing more products. And what I mean by that is, say I have, and we're just going to use A, B, and then C plus energy. And in this case, your energy this is an exothermic reaction. Okay. So in my exothermic reaction, what I'm doing is it's kind of like I have my energy as my product. So if I increase my temperature, now my equilibrium is going to be off. I'm going to be down here. So I need to shift to the left. I'm going to do the reverse reaction. Now, if I have an endothermic reaction, I would have, say I have A plus energy yields C plus D, okay? And so in that case, if it's endothermic and I add energy, now my seesaw is going to be like this because I've increased this side. So what am I going to do? I want to shift to the right. Okay. And same as with the concentration. If I remove energy, if I drop the temperature, then I'm going to shift to the side with the energy. If I drop the temperature, I'm going to shift to the side with the energy. Now, pressure is a little bit different. Increasing the pressure will cause the reaction to shift toward the side of the reaction with the least number of moles of gas. And the reason for that is because if you go to the least number of moles of gas, then you're going to reduce the particle collisions with the side of the container, which is going to reduce the pressure. It's going to ease that pressure situation. Now, some reactions are spontaneous and some are not spontaneous. So, I really quickly wanted to talk to you about spontaneous versus non spontaneous reactions and free energy. Free energy is the energy that is available to do work in a process, but you have to understand that no process is 100% efficient. I mean, everybody wants to work towards 100% efficiency, but that's not reality. It's not something that truthfully exists. So, in reactions, we have spontaneous reactions and non-spontaneous reactions. Spontaneous reactions are ones that are going to occur naturally and favor the formation of the products, okay? Occur naturally and favor the formation of the products. All spontaneous reactions are going to release free energy. Now, non spontaneous reactions do not favor the formation of the products at specified conditions, and it's not going to occur naturally. Now, in nature, in general, things tend towards disorder. This is the second law of thermodynamics. So, the second law of thermodynamics is that everything's going to turn messy. Okay. And so you start with organization and then everything gets messy. Think about your room at the very beginning of the week. Maybe on the weekend, you are forced to clean your room and you have to get your room nice and clean and perfect. Okay. By the end of the week, does your room look that nice and neat and perfect? Probably not. You might have clothes on your floor, or you might have a messy desk or old dishes in your room if you're allowed to eat in your room. But things tend towards disorder, and then you have to do work to make it more orderly. Okay, so entropy is going to increase when going from solid to a liquid. If you think about it, you've got your particles, and your particles are very close. And then when you go to a liquid, there's more disorder. Things are farther away. Entropy increases when substances are divided into parts. So, say I had a glass jar and I dropped it on the floor. It shatters. Things went to an insane amount of disorder very quickly, right? So, when things break into parts, entropy is increased. Entropy increases when number of products in moles is greater than the number of reactants in moles. So, in this case, with H2O, 2H2O produces 2H2 plus O2. I'm going from 2 moles and I'm going to 3 moles. So entropy is increased. Also, entropy increases when temperature increases because things are getting more disorderly, they're going faster, they're getting farther away from each other. So that's the very last thing that we're going to end with today, except for we're going to take a look at just this real quick practice problem. So in this case, this is going back to Le Chatelier's principle. What happens as you add Cl2? Well, if I add Cl2, I'm adding to this side. Okay, so if I add Cl2, think about it in terms of our seesaw. I've added to this side. What am I going to do? I want to shift left. Or what that means is I'm going to shift towards the production of the reactants. What if I decrease or remove temperature? So if I remove temperature, I'm getting rid of this. Okay. So what did my seesaw do? My seesaw did this. Okay. What do I need to do? I need to shift left. So I'm going to shift left, or I'm going to increase the production of my reactants. What about increasing pressure? If I increase pressure, I shift to the side with the least number of moles of gas. Well, here I have 1 mole and here I have 2 moles. So I'm going to shift again. I'm going to shift left in this case. What if I remove PCl3? So if I remove PCl3, what have I done? My seesaw PCl3 has gone up. Okay, it's up here because there's not enough weight weighing it down to keep that at equilibrium. So what do I need to do? I need to produce more PCl3. So I'm going to shift right, or favor the production of the products. Okay, so hopefully that kind of helps you in your knowledge and understanding of what happens if I apply stress to a situation. If there's stress in a situation, we want to shift the reaction to fix that stress, to make everything hunky-dory, to make everything happy and stable and wonderful. If you have any questions, please be sure to reach out and I can answer those questions.